The angle problem. We will see this one. So we already solved for Luke and the Ewok, reeling him in. Part B says, at what rate is the angle between the line and the ground changing when there's 20 feet of line out? So it's the same exact setup as number 1, but now we're looking for a change in angle. So again, I'm going to draw my picture. Anytime you can draw a picture, it's always best. We know that C is 20, B is 12, and this is my constant, so I'm just going to leave it as 16 right there. Okay. Remember, this is my constant, so I like to leave it as such. We're looking for the change in angle between the line and the ground. Be careful, this is already 90 degrees, so which angle are we looking for? A lot of people get it wrong. They pick up here for some reason. But remember, this is the ground. So we're looking for this angle. So if we list, so we already have pretty much everything given up here already. So my hint I want to tell you, when you're finding anything, we're trying to find d theta dt. The biggest hint I can tell you is we are going to use a trig function. Okay. Now, there are 6 trig functions we can use. Any of them will get the right answer. Every single one of them will give you the right answer. But you do run the risk of product rule and quotient rules with trig. So to avoid that, I will say when you pick your trig equation, when you pick your trig, use the constant. Okay? Use the one with the constant. So if I'm looking at this angle over here, I have a choice. I could use sine theta. I could use tangent theta. I could use cosecant theta. And I could use cotangent theta. So these are the 4 that are going to work best for us. Now, obviously, cosecant, a nasty little derivative that is. So I'm probably not going to use cosecant. Matter of fact, the easiest one of these is probably sine theta. That's my easiest one. So I'm going to pick the easiest of them. And if I look at sine of theta, you might remember, is the opposite over the adjacent. But remember, my opposite side is my constant. So I can just write this as 16 over my adjacent side, which is b. Now that's over the hypotenuse, which is c. Oh man, I just messed up. Don't tell my students I did that. Sorry. Over the hypotenuse with the c. Now remember, the 16 is a constant, so I'm just going to leave it like that. This changes. Remember, as we're reeling the Ewok in, the length of the line is changing. So I can then rewrite this as sine of theta equals 16 times c to the negative 1. I'm going to have to take the derivative. All right, so let's be very careful when we take the derivative. Okay? The derivative of sine is cosine theta. Don't forget, this is the part you're going to mess up on. Take the derivative of theta with respect to t. d theta dt equals, and this becomes, we should get really good at this, negative 16 over, that becomes c to the negative 2, or c squared on bottom, times, and again, you need to take the derivative of c as well, dc dt. There's your derivative. This is a hard one. All right, let's take a look at what we need. I know dc dt, we got that above up here, right? dc dt was negative 2, okay? We need cosine of theta. Now, at this point right now, some of you guys are thinking, Mr. Wernow, we got to do trig stuff. You don't. This is a right triangle. We already have all the information. Cosine of theta is the adjacent over the hypotenuse, which is 20, 12 over 20. And then I can just plug everything in. 12 over 20, d theta dt is what I want. Negative 16 over c squared. So that's 20 squared times dc dt, which we know is negative 2. If I simplify this, if I start solving, I'm going to go ahead and solve this. I would get dc dt equals 32 over 400 times 20 over 12. And honestly, if you leave it like this, that's okay. But let's go, that's not dc, it's d theta. So therefore, our d theta dt, if you simplify it, you would get 2 over 15 if you reduced it. But let's talk units. We are in math. We don't use degrees. This is in radians per second. And we would think it would be positive because as we're moving towards, this angle is going to grow. So we can say the angle is increasing at a rate of 2/15 radians per second. Right there. All right. Good question to know how to do. All right. So go on to part 3, and we're going to take a look at the shadow problem.